In this video, we will take a look at the engineering constants analysis in its various forms. And at first, let's take a look at an overview slide that shows us the entities that are covered. So you can do engineering constants analysis for materials, for plies, laminates, zones, and elements. And the two images on the right side, they illustrate both the numerical results that you can see nicely formatted on the very right, and then also an example for line plots as you can get them in engineering constants analysis. Now, before looking into more details, so going through the various entities and the available results, let's also take a look at the supported ply types. First of all, if you have been a long time HyperWorks user, you may know that originally there was just the ply itself, and maybe you have seen the shell-to-solid divider that's here in the very bottom. Now, to be able to concentrate on the, let's say, nominal data of a ply, so the nominal thickness, orientation, and the assigned material and shape, we have been introducing the various ply types to cover the different behaviors better. So the first one here on the list is unidirectional. There's no change from legacy ply behavior, which means you essentially put all the nominal data in. You don't need necessarily any drape data, but of course you can drape those plies as well. Next one is the homogenized weave. And again, no change from the legacy ply behavior. This is, as you can imagine, used to model fabrics where the scale of the material is homogenized through the thickness of the ply. Here we assume the modulus in material 1 and 2 direction to be the same. When you start draping such a ply, this will lead to conversion to unidirectional weave, which means the material data is converted such that you get unidirectional plies that when you build them with a quarter thickness each and in 0, 90, 90, 0 to begin with, will lead to equivalent material behavior. But the benefit here is that once you have your draped material and you have a shear on your original weave, you can actually map that shear behavior much better, because now when you have this unidirectional weave, you can reproduce behavior that is, let's say, not 0, 90, 90, 0, but 10, 85, 85, 10, which might happen in some areas of the model when you have draped the material. So when you're working with unidirectional weave, you require a drape table. Similarly, when you're looking at wound plies, that's meant to be used for models that basically originate in a winding simulation. That also means that the definition of the ply itself might be just, again, by a nominal orientation, but when you wrap the ply around, the orientations vary spatially as the toe is wound onto the tool, and hence you need to cover that, and also the potential covering of the ply over itself once it's wrapped in a drape table, and that's done nicely in our software as well. The last one that we haven't covered yet is the core, and again here no change from legacy ply behavior. The idea behind this is to mainly focus on the core with its nominal thickness, and then covering the various ramps or changes of the thickness in a drape table. Let's start with opening our model. You can find the model in the link of the playlist description. So again, we will have to start opening ourselves the composite browser that holds all our composites related items. In this case here we see a laminate with a few plies and also a few unstacked plies, and of course we do see our materials in here as well. For better visualization, I like to use the view that shows the plies as independent layers and also shows the 2D shells as with 3D thickness. So in this case here you can already see that now we can see the plies much better than before. Let's focus a little bit more on the materials now to get to our material engineering constants. First of all, you can see that I have a selection of materials here and they are using different card types. So I got Mat8 materials, Mat9 ore, which have then the full 3D description. I do have material data for my different woven materials, and I also have a multi-scale designer material here that's also supported for the engineering constants analysis. Maybe in case you haven't worked with those before, you basically just create a material, give it a name that references an assign card, and then once you're in your cards, you can just right-click, create assign, which I've done in this model already, and then it's only about picking the correct type, MatMDS, giving the same name as before, and then referring to your MatMDS file. But now finally to the actual analysis. So I just mark them all and right-click, hit Analyze, and we'll see the effect of the different cards and what's supported in there when we go through the different materials. First of all, it starts with the material data always up top. So if I swap, we can see that ID changes, the name and the card image, but also the values. So up top here also is engineering constants, summary and thermal expansion coefficients, followed by the allowables. In this case, Mat9 ore doesn't have a direct assignment of allowables. You would need extra cards like MatF, which are not supported at the moment. But for Mat8, you can put the allowables directly in forms of stresses or strains. And we'll also show them then in both correspondingly. As I mentioned, MatMDS is supported as well, so multi-scale designer material, and here we can also see that we get the engineering constants, thermal expansion, and full 3D matrix depending on the material behavior. Again, allowables are not included, but that's due to the nature of the multi-scale material actually being able to decompose the stresses one scale deeper than what we normally do on ply level. And then of course you can switch to the different mode, that is the plot in this case. And for example, we could go and pick the glass epoxy, and once the homogeneous weave and once the uni weave material, and we'll see how those are basically differing in nature. So the homogenized weave has this typical 0 at 90 bump in there, and the uni weave has the typical unidirectional behavior of just showing the tip at 0 degree. And same goes, well, you can combine different graphs with each other. You can also look at the alphas or the different items of the cube matrices here. For the engineering constants or the plies, I could essentially go the same way, just pick my plies and then right-click analysis, engineering constants. But this time I want to go through the actual analysis entity. So I'm creating the analysis entity here. And then I'm selecting the correct type, which is engineering constants, followed by the entity of choice, in our case the plies. Now I could pick plies from the GUI here, or from the browser, or if I use the advanced selection menu, I can also grab them from here with the various additional features potentially. So let's run this engineering constants analysis. And what we see is similar to the materials, essentially. So we get engineering constants, thermal expansion coefficients, 2D, potentially 3D matrices. The difference is that all the values that you see are actually computed at the given orientation and obviously thickness. If I'm swapping to the plot and just switching on the line plot for fiberglass 1 in EX direction, then we can see the same number here. So if I hover, I can get a detailed info about the ply and the actual number shown in the line plot. And the difference here now is, again, if I have my 45-degree ply, then this is orientation change. So no change means this is the value for the 45-degree angle ply. And if I wanted to see the values for a 0-degree ply, I would have to go minus 45 degrees. And this is also where I expect the top to be for such a unidirectional ply. More interestingly, if I swap to homogeneous weave and unidirectional weave, we can see that the shape is the same, but the shape wasn't the same when we just looked at the material. So now the reason for this is that internally we already use this unidirectional weave material to construct the woven material underneath from the warp and weft layers. And that's why what we see here, now if we go to unstacked plies, we can see the homogeneous weave at 10 degrees, so that's the minus 10 tip here, and the same for the uni weave. So that's how that affects the ply properties. Finally, we have the laminate engineering constants. And if we go scroll up here to our laminate and basically just do our right click analyze again, we can immediately see, okay, this laminate has two different zones. We will see again the data for each zone with the stacking sequence and how it changes, also the thickness and the number of layers, and all the values underneath, starting from the laminate matrices, engineering constants in plane bending, and also the zero curvature values, thermal expansion coefficients, homogenized matrices, and in the very bottom, also out of plane shear properties. Now, there are a few rules to what kind of laminate will be analyzed. In this case here, all the plies had a shape, so we can internally produce the zones, and maybe to visualize them, I can show you here a little trick, because now you can see there's two different zones, and if I swap to the zone view, we can actually make those match. So we got the yellow one up here and the green one on the other side. And I can also just right click and analyze from here, and then I will get the properties for just this one zone that is currently selected. But now, what happens when there is a ply in there that doesn't have a shape? Well, the answer is simple. If I remove the shape here, I rerun the analysis, then it can't produce the zones, which means what we will get is the property calculation for the full stack as it's given in here. So just the layers as they are, regardless of their shape. as I wanted to show you also the behavior of the different ply types, let's remove those plies from here, put them to the unstacked, and let's import those ones to our laminate. They all do have a shape assigned, so that should be straightforward. And maybe I'm going to change the last one here also, that we can more easily see what's happening. So first of all, I can go right-click engineering constants again as before. And now what we'll see is we have our layup here. The homogenized weave shows up with 10 degrees. Then we got our uni weave, and remember, this one is the one that has a uni for warp and weft. So modeling this one here with the 15, that is the nominal value. Then 15 plus 90 makes 105, 105 again, and 15. So to build our full warp and weft woven. Then we have a wound layer. Again, this one here only showing the nominal value at 20 degrees. Our shell to solid divider, which shouldn't play a role in our analysis, and it does not. So 0 thickness in here, and it doesn't show in the list. And we got our core in the very end here, also with the 25 degrees. To illustrate that a little bit more, we can review all the plies separately. And for that, let's enable the orientation review here. So we can first see, okay, our core material has the 25 degrees, but the main focus here is actually on the thickness and the basically the ramping between the different thicknesses on the model. Then we have our divider slide here. Doesn't have a thickness, doesn't show in the list as we've seen, so nothing really important to review. We got the wound ply, and the wound ply itself, it has one layer here, but it can have n different slices, with then each the corresponding yellow arrows here for the orientation. As you can imagine, this case here is not coming from a filament wound model, so this is more or less just to illustrate that, okay, you have to have a drape table, and then values are going to be shown correspondingly. The homogenized weave also basically has just the one direction here, the 10 degrees that we can see. There is no drape table assigned, but if I would drape this one here, it would actually be converted to unidirectional weave with corresponding material data in the UDs and also with a corrected warp and weft. And this is basically what happened here in the uni weave. So there I can see my two different directions. We had the 15 and 105 degrees, and this again then draped on the model, so the values are going to be changing back then. So if I switch that back off again, and we go to an analysis with the elements as a basis, then we can easily see the effects there again as well. So I'm going to pick one element here, one somewhere in the middle, and one from the very beginning here. Okay, and run. And now this is sort of what we expect. If I scroll up back here to my layers, we can see we got 3 different elements, and the orientations for the homogenized weave stay the same, but the ones for the UD are actually adjusted from the original 15 and 105 to different values depending on the position in the model. Like this is the most original one with 15 and 104. We got our wound ply, which shows changes, and the core here, which essentially has the same orientation everywhere, but the thickness is changing. One last bit. Of course, you can also, in the laminate engineering constants, swap over to the plot. And again, this time we are rotating the whole laminate and providing you the properties for that. So that's the laminate properties in material 1 direction. If you wanted to see the laminate properties in material 2 direction, you would have to go to the plus or minus 90. And yeah, there you have the selection of all the rotated properties, also the flexural properties, zero curvature, and the thermal expansion coefficients.